we have two objects, two rotating objects, in this case two circles, with the same axis. They're rotating about the same axis, but they're here's the axis, goes through the center of both, separated by some distance s. We can work out their relative angular positions, velocities, and accelerations from given information, just as we did with the linear problem. So that we get a theta 1 and a theta 2 with an angular acceleration alpha 1, a b1t and a c1, an angular acceleration alpha 2 with a b2 and a c2. And if we're given initial conditions analogous to the ones that we saw previously, we just do exactly what we did previously. We can take derivatives of these and get the angular velocities. So if we have initial information on our angular velocities, that's going to allow us to determine v1, assuming we already know alpha 1, and so forth. Okay, so again, we obviously can express b1, c1, b2, c2 in terms of the quantities that were given in the worksheet. The relative angular position, now if you're driving down the road and a car is going past you, moving faster, you'll see his relative velocity being positive. His velocity being positive relative to yours. Well, assuming positive direction is forward, then you would just subtract your velocity from his. So it's his velocity minus yours is the relative velocity as you observe it. Here, relative angular positions of these two wheels is just the relative angular position is angular position, relative position of wheel 2 with respect to wheel 1 is theta 2 minus theta 1, the theta 2 function minus the theta 1 function. Just completely analogous to the problem of traveling down the road and figuring out the relative speed of that car that's going by you or that you're going by. Okay? And then, of course, you would get your omega 1 and omega 2 by taking derivatives. And the relative velocity of number 2 with respect to number 1, wheel 2 with respect to wheel 1, is just the difference of the two angular velocities. Now, we don't do too much with this. We want to move directly to the angular positions. Okay, so if the angular positions are theta 1 and theta 2, I want to know in 3 dimensions what the relative positions of the points on the rim at angular positions theta 1 on this disk and theta 2 on this disk. In terms of those two angular positions, what's the displacement from the point on this rim to the point on this rim? Well, if theta 1 is the angle on disk 1, which has radius r1, then the x-coordinate, if we introduce an x-axis this way, a y-axis this way, and let the z-axis be the common axis about which the two disks are rotating, then, okay, if we're at the theta 1 position on the rim, then we're at x equals what? r1 cosine theta 1. Now, if you're not very conversant with the circular model, get used to it. And y1 would be r2 sine theta 1. Implying a position vector, if we take the origin of our coordinate system, as I've drawn it here, at the center of the first disk, okay, position vector is then going to be what? r1 cosine theta 1 times the I vector, because of course the I vector is in this direction, and you multiply that by the r1 cosine theta 1 to get a vector along the x-axis, and then the y component times the j vector. Now we have a vector that I'll call the r1 vector. In the bracket notation used often in linear algebra, this could be just expressed as a row vector. Now, I didn't have a lot of room to write this, but just r1 cosine theta 1, r1 sine theta 1, 0. The x component is r1 theta 1, the y component is r1 sine theta 1, and the z component is 0 because disk is on the origin. This disk is centered at the origin. For number 2, your position vector would be similar, except you'd have a component now in the k direction, because every point on this disk is a distance s from the origin. Now, the way I pictured it, this thing is in the negative z direction, so for this picture, you would add a negative sk. So you would start here, you would go through a negative sk, which would get you to the center of this disk, and then you would go r2 cosine theta 2 times I, and r1 sine theta 2 times j, and there you would be. So, this is the vector, and it could be expressed as a row or column vector. In this notation, we're going to call the vector r2. The relative position is r2 minus r1, and the distance between the 2 points on the rim is just found using the Pythagorean theorem, if we're used to that, or just as the dot product of the relative position vector with itself, well, the square root of that dot product. I say this because one student in the class has had the linear algebra, not multivariable calculus. So either people are rusty with the linear algebra, even though they're doing multivariable calculus, or they're conversant with the linear algebra notation, but not the multivariable calculus notation. In any case, everybody has been through linear algebra and will understand, if they think about it, that if we express r1, let's say, as a row vector and r2 as a column vector, the dot product, which we haven't covered yet in linear algebra, of those two vectors is just the row vector multiplied by the column vector. So anyhow, that's how we get the distance. And we can just directly apply the Pythagorean theorem as well. I didn't do that just because of not everybody having done that a lot. Again, we've got now a general theory for relative motion of two disks moving at whatever angular velocities with whatever initial or whatever conditions at whatever time, and with given angular accelerations. So we can do all kinds of things, including find the distance function.